Welcome to CSAI Think Tinker Learn. This video is part of our new system design series, which is essentially for system design essentials, where we cover complex architectural topics at a high level to keep the lessons concise. For a full article and technical diagrams, you can visit our companion website. The link will be in the description. This will be this website here. Articles will be listed here. You can actually take a look at these. This is a work in progress. So as and when the articles keep coming, you can have a view of them and I'll continue making videos on them. Now, these videos, the one in this particular essential series, are designed to introduce the core concepts very quickly. If there is a specific pattern, like the internals of a sliding window algorithm, that you want to watch a dedicated video on, let me know in the comments. And now let's get into the mechanics. To understand why we need a gateway, we have to look at the broken state first. Without a gateway, every microservice in your fleet is forced to defend itself. This is a baseline failure in system design. If a single bad actor sends 100,000 requests per second, they can take down your entire backend simultaneously because your services are fragile and exposed. We need intelligence at the bottom, a system that authenticates identity, shapes traffic, and routes requests before they ever touch a backend resource. Routing is our first tier of defense. We have path routing, where the gateway inspects the URL. This is the ink mechanical switch, where the gateway might strip a prefix like slash users, so the upstream services stays unaware it's even behind a gateway. Then there is a header routing, the professional tool. By reading the metadata envelope, we can route traffic to completely different backends. This is how we achieve clean API versioning and SaaS multi-layer tenancy without polluting the URL structure. Tier 3 routing moves into weighted canary deployments. This is the ultimate safety mechanism for modern infrastructure. Instead of explicit rules, we split traffic by percentages. We send a small canary, say 5% of real traffic, to a new version. If error rate and latency stay stable, we gradually open the valve. This is how you ship code on a Friday afternoon without breaking production for every single user. Next, let's look at the auth pattern one, API keys. This is a simple stateful secret. The gateway performs a sub-millisecond cache lookup, usually in Redis, to allow or reject the caller. While great for fast server-to-server internal calls, it's a monolith trap. API keys grant identity, but lacks granular scope. You cannot easily say this key can read orders but not create them. It's an all or nothing key to the castle. Auth pattern 2 is JSON Web Token or JWT. Think of it as a self-contained passport. The gateway verifies the cryptographic signature locally with zero database hits, making it perfect for microservices call scaling. However, notice the revocation gap. Because verification is stateless, you can't easily untrust a valid token unless its expiration claim is reached. In production, we mitigate this risk with short 15-minute expirations and a Redis-based blacklist for compromised keys. Pattern 3 is the OAuth 2-ring model. This is exactly the answers interviewers want to hear. We separate concerns. The outer ring is authentication, handled by the gateway to verify who the caller is. The inner ring is authorization, handled by the microservice to decide what the caller can do. Only the user service knows if user A is actually allowed to view user B's data. Never duplicate this logic. Auth at the gateway, Auth in the service. Here's the synthesis. The authentication trust matrix. A MAANG-level gateway doesn't just choose one of these. It uses all three simultaneously, mapped to different trust relationships. API keys for internal M2M, JWTs for standard microservices users, and OAuth2 for third-party delegated access. Understanding which to use for each relationship is what separates senior architects from juniors. Now, let's talk about throttling. Pattern 1 is the fixed window. Time is divided into discrete intervals, and request increments a counter. If the limit is hit, we return a 429 too many requests error. The danger here is the boundary trust. A client can send 100 requests at the very end of one window and another 100 at the start of the next. Technically, they followed the rules, but they just hit your system with 200 requests in 2 seconds. Simple stopwatches fail in production. To fix this, we use buckets. The token bucket is the industry workhorse. It accommodates bursting by letting idle clients accumulate tokens to span all at once, perfect for batch uploads. The leaky bucket is for downstream protection. It ignores the client needs and cares strictly about protecting fragile legacy services that cannot handle spikes, smoothing output to a constant rate. Token bucket asks, can the client send? Leaky bucket asks, can we process? The production standard is throttling pattern 3, the sliding window. This is the principal engineer choice. It combines the over memory efficiency of the fixed window with the burst resistance of a sliding log. Instead of storing every timestamp, we store just two counters, current and previous window, and calculate a weighted estimate based on the overlap percentage. It smooths the data curve mathematically without blowing up your Redis memory footprint. In the real world, you don't have one gateway. You have dozens behind a load balancer. How do you enforce a global rate limit? You have three options. Number one, centralized Redis, which is accurate but adds network latency. Number two, local plus async, which is extremely fast but only eventually consistent. Number three is peer-to-peer gossip, which is complex but avoids single point of failure. For most interviews, pitch option 2. Acknowledge the consistency trade-off to prove you understand distributed systems. When things really go wrong, we use the circuit breaker to protect the downstream. If an upstream service fails continuously, the gateway state machine flips to open. It stops forwarding traffic and immediately returns a 503 service unavailable message. This gives your database or microservice time to recover without being drowned in a flood of retries. Don't kick a service when it is down. Give it a chance to breathe. Let's synthesize this into a middleware pipeline gauntlet. The layer must execute in an exact non-negotiable order. Auth, throttle, route. Why? Because you cannot rate limit by a specific client ID if you haven't authenticated them yet. And you don't want to waste expensive CPU cycle routing a request if you are simply going to drop it for throttling half a millisecond later. Build your fast API or go middleware exactly like this. Finally, we have observability. A gateway without telemetry is a black box. A gateway with telemetry is a control plane. Position at the entry point, the gateway emits rich signals, structured logs, route labeled RPS metrics, and injected distributed traces. Design this well, and your whole architecture gets to breathe. Now, I have a question for you. Which of these throttling algorithms are you currently using in your production stack? And have you ever had a boundary burst take you down? Let's discuss in the comments. Don't forget to like, share, and subscribe, and visit the GitHub pages for more articles like this. Until next time.